just let me load like the presentation, the slides, because it's a bit slow because of the image qualities and the image resolution. So it takes a bit of time to load each slide. But once it's loaded, it's more fluid. So I would say just wait until the whole presentation is loaded, then we can start.
Okay, should we start?
That's what I was saying is that I need to take a bit of time to load all of the slides because I believe that the resolution of the images here are a bit.
Okay, Jorge, your voice is not really clear. They are like parasite.
Okay.
You're using the mic?
Sorry?
I say you are using the mic?
Yeah, I'm using computer audio, but the thing is,
because
the
they are like,
presentation is.
Yeah, it's not very clear. It was before, but not now.
I believe it's because of the presentation. It's slowing down the tag, you know. So you know what I mean. The presentation is slow. So because of this, it affects the Zoom quality. Okay.
Okay, should we start?
I believe we can start now. Can you hear me properly, like now?
Yeah, honestly, still the voice is not really very clear. It's like there are some noise.
So how much time will I have for
Around 1 hour.
an hour and a half? Okay, that's fine.
Okay, so I start introduce you.
Okay, that's fine.
Okay, so welcome everyone in another session of AstroTalk NOC session. And today our guest for AstroTalk is the amazing astronomer Jorge Maidana-Montiel from Paraguay. And in the frame of Asteroid Day for the 30th of June, today he's gonna give us a talk about how do we detect asteroids. So with Jorge, he is an amateur astronomer with a big heart of outreach activities, and also he came from computer science background, and he had in fact a master's degree from the Royal Holloway University of London. So Jorge, he is one of the amazing amateur astronomer in Paraguay, and today he gonna give us how a talk, a very interesting talk, how we detect asteroid and how we study them. So Jorge, you can start.
Thanks for having me today. So presentation is just loaded. It's in Spanish. I'm sorry about that, but I'm going to translate each slide as we go by, and um, so actually the presentation is about the whole of detection of asteroids. So it has three parts. The presentation has three parts. Where I'm going to go through the first part, which is what actually are asteroids and what it makes it different from other objects, and then I'm going to move to the detection of asteroid, properly talking. So this presentation was written by the guy named here Waldemar Villamayor Benialvo, which is the founder of CEPIA, which is where I came from in Paraguay, which is our organization, and it was written 2 years ago for Asteroid Day, but it's quite uh, up to date, so it's fine. And so let us begin by saying that asteroids and minor planets. We're going to talk first of this, and why do we want to like detect asteroids? So why is it important to detect asteroids? Because massive asteroids can cause massive extinction, as it happened with once 66 million years ago, which is stated in the Alvarez hypothesis, which was written by physicists Luis Alvarez and Walter Alvarez. And they say, or in the hypothesis is stated that um, it's likely that an asteroid or a comet of 10 or 15 kilometers wide caused this global catastrophe in the period called Cretaceous Tertiary period. And why do they think it's an asteroid, or it was an asteroid or a comet? Because there is a boundary layer on Earth and on on the marine cover of Earth, and on the Earth crust, which is composed of iridium, which is a material that is found mainly in asteroids and is rare in Earth. So they think, well, this this thing might have been an asteroid or a comet, and then the massive extinction caused a huge impact in global environment, and it caused what we call an impact winter. However, uh, that's not unusual because we recently got an event like this in Russia, in a region called Chelyabinsk, and so this event we call the Chelyabinsk event, and it happened in 2013 when there was a super bolide which entered the Earth atmosphere, and it is thought to have been of 20 meters wide, only 20 meters, but it's big actually. And well, this caused a huge air burst on the surface of Earth, but it fragmented and it disintegrated on the air, so that it did not have an impact crater. Uh, this just happened like 7 years ago. So we should be like saying, we should be warned that this can happen at any time. And well, next, um, from where do asteroids come? So when the solar system was developing, um, so this slide talks about the origin of the solar system actually. So we saw by the works of Swedenborg, of Descartes, and of Kant, and of lately of Pierre Laplace, that the solar system originated in a high, or let's say a cloud of gas, which collapsed because of high density in a region. So it created the sun. And this is what we can see here in stage 2. And what happened afterwards was that the planets were created, and whatever else came from this development of the solar system was the asteroids and anything else. So planets got already, and then the asteroids. So where do we find asteroids? We would find asteroids after the orbits of Mars, or between, let's say, between the orbits of Mars and Jupiter. So we have there the main belt of asteroids, and the distance. This is, I believe, it's 2 astronomical units. This UA here is astronomical units in Spanish, actually. But we also got them in the Kuiper belt, which is after the orbit of Neptune. Also, this is some of these objects are called trans-Neptunian objects. This Kuiper belt is 50 astronomical units away of, of the sun, and as well we got a whole cloud, which is called the Oort cloud, or the Edgeworth Oort cloud, mainly after the Dutch astronomer Oort. And this cloud covers the whole of the solar system, and is at a distance of, or covers a distance of 1 light year, which is 63,200 astronomical units. Okay, so after this, so we can know where do asteroids come from. So let's start with some definitions of what exactly, so that we can get to what exactly is an asteroid. So we know planets, according to the International Astronomical Union, has three um, three main conditions that they should satisfy to be called planets. So they have to orbit around a star, they have to be of an spheric shape, and they have to clear the neighborhood. And so major planets, of course, they do this. And so we know that, for example, Pluto cannot do the lattice, which is clearing its neighborhood. And so it's accompanied by Eris, Makemake, and Haumea, which are what we now call dwarf planets, as well as Ceres. And then, so what makes a planet? It makes that it orbits around a star, that it has a spheroid shape, and it cleared its neighborhood. And well, what else? We got as well natural satellites, or what we call moons, and they orbit around a planet. So we got here many of the solar system moons. There are many more than this, but we got the moon, which is called moon, and then we got in Mars, we got Phoebus and Deimos, and then in Jupiter we got Europe and Ganymede and Callisto, which are the Galilean or Jovian satellites, which were apparently discovered by Galileo like 400 years ago. Then we got in Saturn, we got all of these: Mimas, Enceladus, Tethys, Dione, Rhea, Titan, Hyperion, Iapetus, and Fifth. And Uranus, we got Umbriel, Ariel, Miranda, Puck, Titania, Oberon, and okay, we got Neptune, we got these three here, and in Charon is of Pluto, and Eris is um, Eris is again, Eris is a dwarf planet like we have seen before, and it has a moon called Systomia. So this is the Earth here is, I believe, is in a scale with respect to these objects. Again, the trans-Neptunian objects are objects which orbits are farther than Neptune, and they are icy objects. They are in the Kuiper belt, and perhaps we got as well some comets in the Oort cloud. So here are some Transneptunian objects. Again, Eris and its moon, Dysnomia, then Pluto and Charon. Then we got all of these weirdly named objects. And as well, Sedna, Orcus, Core, and Varuna, all of them are Transneptunian objects. If we look carefully at them, we can notice that spheric, they have an spheric shape, and um, but they are not hover planets, or they are not cold planets. Again, so now we come to see what is a minor planet, or what's an asteroid, or a small body, or as well a planetoid. So they are composed of, or they are rocky, they are carbonaceous, and they also got metal. Um, Mainly we would find them in the main belt of objects or of asteroids, which is after the orbits of Mars, or between the orbits of Mars and Jupiter. And their size is between 1 kilometers wide to 1,000 kilometers wide. So we got here a picture of many asteroids. So all of these asteroids are depicted here are asteroids that were visited, or there was a flyby of proof to to these objects. So this asteroid, which this is an actual picture, this is not a model, is taken from 21 Lutetia, which was visited by Rosetta mission, the Rosetta mission, which is a recent mission um, from the European Space Agency. And then we got Gaspra 951 Gaspra, which was visited by Galileo, the Galileo proof. And then again, we got this was detected by NEAR, I believe. It's not much clear there. This asteroid called 9969 Braille was visited by Deep Space in 1999. This asteroid in front was can clearly see, but I believe is Stardust mission in 2002. And Rosetta, again in Rosetta, visited this asteroid 2,867 times, and Galileo visited this asteroid called 243 Ida, and Dactyl as well by Galileo, which is in here. All of this is scaled, I believe. And then the asteroid Matilde, 253 Matilde. Um, I believe I mentioned all of them already, but no, we got this Vega 2 mission in 1986 here. Um, this is a comet actually, and Borrelli as well by Deep Space, and the comet Wild by Stardust. So, um, so this is the purpose of showing this is just to see the difference between a comet, somehow to see the difference between a comet and an asteroid. So we know the comets lives in the Kuiper belt, or in the Oort cloud, and their size is of 10 to 15 to 50 kilometers, and they probably compose 80% of them of ice, and the rest is silicates and organics, so 20% of them. So again, the same image on the page. I have already shown them. So these again, these were objects visited by space proofs. Uh, Somehow visited because in some cases it was just a flyby or pictures taken from from a very distant point. So other minor or other small bodies that we can talk about are meteoroids, which can be composed of ice or rock, but it can be rocky. So we got that they got a solar orbit, and they are bigger than a dust, or a grain of dust, until 10 meters. So they can have between uh, they can be of size between a small grain of dust to 10 meters. That's a meteoroid. A meteor properly is the light produced by a meteoroid that enters the atmosphere or the atmosphere of other planets. Then we got fireballs and bullets. A fireball or an bullet, a meteor that is very bright and can be produced by a meteoroid that reaches the lowest, I would say, the lowest is in English should be so in the atmosphere. If you reach the lowest point in the atmosphere, so that would be a fireball or that would be a bullet. And a meteorite is a meteorite that did not burn completely and reaches the surface of the Earth or a planet. So here we can see the difference because we got a fireball they are brighter than planet Venus. They are visible even on a day. They can be visible. So we're talking about fireballs and bullets. The bullets split or fragment and they can explode in the atmosphere, or they do explode in the atmosphere. That would be the difference between fireball and a bullet. So let's begin to talk about objects that are near the Earth by means of the orbit. So we got an object whose orbit is or whose perihelion is less than 1.3 astronomical unit is called a near-Earth object. And so we got asteroids with this asteroids which has that orbit. So they are called NEA, and NEC is a comet which has the orbit or orbit at less than 1.3 astronomical unit. And then we got some satellites, of course, the satellite of the Earth and Trojan asteroids. And as well, we got meteoroids that can orbit at that distance. So any object whose orbit is in the neighborhood of 1.3 astronomical unit from taken from the Earth can be called like near Earth object, and so we got near Earth asteroids and near Earth comets. So again, this is a picture that depicts the main belt. So we got the objects here in green are the main belt. We got the Earth and the planets in the small blue dots here, and anything else like other objects like uh, they can be asteroids as well are depicted in red. The points depicted in red, of course, um, can affect the Earth, so they can cross or orbit. So, as far as we know, in the main belt asteroid, in the main belt of asteroids, we got 750,000 asteroids. This is a number that was taken 2 years ago, but we know that we discover 2,000 asteroids each month approximately, and the whole of the main belt asteroids is only 4% of the mass of the moon, of the Earth moon. So we as well know that I believe the first four objects discovered in main belt asteroids encompasses half of the whole of the mass of the main belt asteroid. So Ceres uh, and I believe Pallas, Vesta, and Aegea. If you take the mass of these objects, then you already have half of the main belt asteroid. So whatever is left of the mass is composed of asteroids that are not as big. So and then we got the objects that are very that are actually can threaten or existence are the near Earth asteroids, and they have particular orbits. There are many of them, and um, here in the picture we can see in here we can see this orbit in this color is called Apollo, and and they have this distribution. So they are one astronomical unit away or the farthest point from Earth is one astronomical unit, and their closest um, so this is their closest point is less than 1.02 astronomical unit. And then we got here this group of asteroids called Aten. This was Apollo. Then we got Aten here. So the Earth would be this blue orbit here, this circular orbit here. So we can see that this is more eccentric, and as well this. So this Aten family of asteroids has the distribution that is shown here, that their um, their farthest point is one astronomical unit, and their closest is less than 1.016 astronomical unit. And then uh, we got here depicted the orbits of the family of asteroids we call Amor, and their closest point would be 1.02 astronomical unit, and their farthest point should be less or equal than 1.3 astronomical unit. So again, so the perihelion is Q, which is their closest point, and aphelion is this big Q here, and A is their estimated major semi-axis, would be in English, I believe. And as well, we got inside, despite this classification here, we got as well a concept of potentially hazardous asteroids, which these are the very asteroids that can threaten or existence. And so their orbit should be less than 0.05 astronomical units of the orbit of the Earth. So, and they as well think they should cross the orbit of the Earth. And if we got an object as defined as this, and whose diameter or who as is as wide as 150 meters and bigger than 22 meters, I believe. If they are in that size, then they can cause a massive extinction. So that's why we got this category, which is called potentially hazardous asteroids. So we know that there are probably 2,000 asteroids which fits in this definition. So let me show you quickly some asteroid detection statistics. So we know that for the size of up to 30 meters, we got 3,340 asteroids. So up to from 30 to up to 100 meters, we got this many thousand, 4,968. For from 100 to 300 meters, we got 4,380 asteroids that are close to Earth, and from 3,000 to 1,000, so 1 kilometer would be 3,962. Um, from there, asteroids are bigger than that. Um, we got only in the hundreds, so we got 886. And well, as well, this is a depiction of the rate of discovery of the asteroid of the near Earth asteroids. So we know that the asteroids that are 1 kilometer wide, they are not. We don't have a lot of them, fortunately. And then we got some asteroids which can be very dangerous, which is the ones that has 140 meters of diameter, and then the rest of the asteroid which are less dangerous. And then we got in the numbers of thousands, we got the ones that fits in the category of 140 meters plus, so they are bigger than that. And then the ones that are 1 kilometers wide are not as numerous. And again, we got many more asteroids, of course. Um, this is a depiction of the asteroids and the survey that has discovered them. So we got linear, which is started approximately in the 1917, 17, I believe, and it's 1997, I believe. And then, the highest rate of discovery was made by linear at that time up until 2005, more or less. And then we got NEAT, which as well was very active in that period. Space Watch as well, which is depicted in red here, you can see. And from then on, we got the Catalina survey, which is a very popular one from more or less 2004. Here we got that. It has a bigger share on the discovery of asteroids. And lately, we got the Pan-STARRS, which is depicted here in pink, and the NEOWISE, which is in this turquoise here, in this turquoise color here. It is just a picture of the share of discoveries. So again, the same, but by the numbers discovered. I believe this was by, yes, what's the same? So strange. Okay, so it was a number discovered. Okay, I think it's yes, because these are the ones that have 1 kilometer wide, and these are the ones that has 140 meters approximately in diameter. So in this size category, then we got Catalina, which was very active from approximately 2004 to very recently, 2017, let's say. And then Pan-STARRS again was having here in this color pink, having the bigger share from 2010 more or less. These are the ones that are important to know. That these are, I mean, the asteroids are important to we detect them because they are in this size and in the size of 140 meters, and they can cause a global catastrophe. Of course, objects of 1 kilometer wide can as well cause a global catastrophe of bigger impact, but they are less in number. So we got like, here in the column, in the graphic, we can see that the numbers of 1 kilometers asteroid 1 kilometers wide asteroids are not as much as the one that has 140 meters. So we got in the hundreds. We got here the asteroids that are 140 meters or more. And this is the rest of the asteroids, I believe, that all asteroids that fits in the category of near-Earth asteroids. And the most lately successful could be, we could say, that this Catalina survey and the Pan-STAR survey. So they detect the smallest asteroids, smallest than 140 meters. And as well, if you are interested, you could see what the size of an asteroid can cause an impact on the Earth. And this is a table that shows size of asteroids and the energy that they can probably release by an explosion. So we could check this in this website here. So anyone is, if it's interested in this, can go there and so this is actually very important. But since we are not going to show all of that now. Oh, sorry. It seems to me that okay, the presentation closed. Sorry about that. Okay. So let's just recap what I have been saying. So we were talking about why it's important why it's important to take asteroids in the first place, and then we move to recent impacts. We go all through the statistics of asteroids and what defines an asteroid. And then I believe we can already go to the detection methods. So again, okay, so this is a last one shot, which is it says here in Spanish says interstellar visitors, and then we got in 2017 there was this object called Oumuamua, which was discovered when it was let's say passing close to the sun, and the International Astronomical Union has to craft a new name or a new category of names for this object, because it was the first time that an object that is not from our solar system came to our knowledge, actually. So this object is called Oumuamua. It was discovered in 2017, and it's important to say it's not an asteroid. It's an interstellar object. Is their technical definition. So again, this is just showing its path through Earth and the moment it was discovered. Was discovered by Pan-STARRS it says here on October 19 of 2017. And let me show you what comes next, which is the detection of asteroids. Okay, so just a second until it loads. So again, we got many categories of asteroids. An asteroid is a rocky object, or it could be icy as well. It depends on where it comes from. So mostly we got rocky asteroids on the main belt. And okay, so let's now talk about okay, let's talk about detection, which I hope I can show you, but it's a bit slow. So when we talk about detection, we talk about plates, we talk about uh, the first discoveries that happened to happen in the 19th century. So, so let's talk about detection of asteroids. Again, it's a bit slow. My apologies because of this. And we got here. Okay. So again, we got many sorts of plates currently, but at the moment when the first asteroids were discovered, the first asteroid discovered was Ceres, which was classified as asteroid on that moment. It uh, was discovered on 2000. It was discovered on 18 in I believe in 1801. Yeah, 1801. So it was the first asteroid discovered. Was called Ceres and was discovered by Giuseppe Piazzi. The methods they use was very different from the ones that we use today. They used to track the orbits of an object, uh, which they thought it would be a planet, and they use something they call the Bode law, and and this that the law states that there must be a planet between the orbits of Mars and Jupiter. So they use these laws to try to find a planet on that place, and what they found instead was the asteroid Ceres. So we can move on the detection of asteroids again. Uh, Firstly, it was with the orbits. However, since the asteroids uh, were discovered in that place, that they discovered many asteroids, and so they find perhaps it's not a planet that we have discovered, they thought. So they started to search for more, and what they found was that there was a whole belt on that place, and that's what we call the main asteroid belt uh, right now. So afterwards, where what we got was the just in the beginning of the 20th century, we just discovered uh, in the moment called a planet, which I'm talking about Pluto. And well, this discovery happened in 1931, and the techniques that were used at that moment are were more rudimentary, I would say. But what they used was they took a picture of uh, let's say a picture, but it's not actually a picture. Is is um, is some sort of photographical plate taken with an uh, an object or a mechanical device called astrograph, and they what they do was uh, uh, they pointed their astrograph or telescope to the region of the sky, and then they say um, they have plates, and the plates of the astrograph were actually um, was actually a chemical reacting with the light that was coming from the astrograph. So there were not actually pictures, but there were glass plates or what we call now photographical plates. And so we got these photographical plates, and what they do for knowing that the object was new in then was to know the exact location of the other objects in the image or in the plate, and then um, they would say, hey, this object here, it wasn't here before. So if you take, for example, two pictures, we have here a picture of, say, January 23 and January 29. So it's 1 week of difference. So if we take this picture and uh, or photographical plate, and then we take a week after we take this other photographical plate, then we could see that there is an object here, but in next play, it's no longer there. The object's no longer there. So it's no longer here, but it's here. So so what had happened? We got a new object, and then what they okay. So let me just show this. So they would say, hey, this is a new object here, and it comes from the plate. So the photographical plates. Uh, so again, the, 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 the discovery was made by a mechanical device called astrograph, and the astrograph take plates, and the plates are by the light that comes from the astrograph that goes through to the plates. They stimulate some chemicals on the plates, and so we got an impression of them here. And so by looking at the difference in different times, then we could say, hey, here is an object here. There is an object here, and then this object wasn't there before. So perhaps this is a new object, and we made a discovery. Again, so how do we do this now? Or how it was done in more recently. So we got a survey called Near Earth Asteroid Tracking. It happened from the 1995, I believe, 1990s or the 1980s. It was a survey done by the U.S. Air Force, and it started taking several plates. These are actually photographical plates because the electronical devices that takes the pictures were just invented, and well, then this image sensor, we popular known them astronomy CCDs, were were invented, and then uh, therefore we got actually images from the sky, and not longer just a chemical simulation or a plate. But anyways, so how do we detect asteroids with near Earth asteroid tracking? What was the method that they used to detect? It was um, by map coloring. So you would say, let's look at the difference between three different images, and then you would say, let's have this field of the sky colored in red, and let's have this other field at a different in a different time, or sorry, at the same time. And then at the same time we colored three of these plates, and then let's look at the superposition between the plates. So let's say, if I do this, if I map color one plate, then another, and then another, and all of the plates are taken at the same time of the same field of view of the sky, then what we got was this. What we got is these three points here. And why is this? Because the object was moving with respect to the field of the stars. So we take this field of view of the sky. We take this field of view of the sky at different time, and then we take this field of view the same field of view at a different time, and then we get this final image, which is called a triplet. And this final image is just a superposition of the different images that we were taking. So now we know that we got a new object because we have colored before several plates, and by superposition we know that they are moving. So the object is moving, and then so therefore by coloring of different plates, by map coloring of different plates, we know that there is a new object here. So we don't longer use this method that is the blink method. This object of the triplets is called the triplets method. So we got two methods already. One of them is by looking at the emulsions in a plate, chemical emulsions in a plate by the astrograph, and then blinking them. So that's called the blinking method. So you got two plates and then you compare them with a mechanical device which was called a blink comparator. And then you could see that there is a new object there. That was the first method we were talking about, this one. And then we got triplets, which is map coloring of the objects, of the plates, actual plates, photographical plates coming from image sensors. And lately we got last method we got is called um, the time lapse of several plates. So this method that takes plates only takes three plates and then color them. But we got a last method, uh, which a friend of mine said that this method, uh, which is as well called the automatic blink, is not good for people with epilepsy because it has an stroboscopic effect. And well, that's because it moves slowly. It appears to move slowly, and somehow it creates the impression that you are you are moving with the object, and it can give you a headache. But this is a method that is called, I believe, is called automatic blink. It's the same as more or less all of these methods resemble each other. But this method it lets you look at different plates at a higher speed. And since you look at them at a higher speed, then it can give you a headache. But as well, you see the object moving in some sort of video or time lapse. And since you see the object moving, then you know that comparing the objects here with the field of stars here, these stars are fixed, of course. And since these stars are fixed, then you know this is moving, then you know this is a new object. And this is called the time lapse um, or the automatic blink. And as well, we got a last method. Let me just show you. This is supposed to be a video. But let me just show you the last one. The last of the methods is a method called radar imaging, which is mainly done, I believe, for near Earth asteroids because they are close to Earth. This is done with a radar. So you take the radar, emit a signal, expect it to come back, and after it comes back, you got an image or a model with the size, with the shape, with the spin of the asteroid, and with the albedo of the object. So it's not shown here, but that's radar imaging. So by radar imaging, you could actually get the shape of the object. So with these objects, there's three objects that I was mentioned before. You don't get to you don't get to get you don't get to have the shape of the objects, but with radar imaging you can get the shape of the objects, and then you get as well, because it's closed, you can estimate its shape, you can estimate its size, you can estimate the spin meaning the rotation that is taking the object, and as well the albedo, which is the brightness that we uh, or the object is reflecting. So I think that's all I have to talk to you about today, and so let's just close this presentation. I don't know if we would take any questions. So so again,
Hi, Jorge. I'd like to thank you
yeah,
for the nice presentation. It was really very interesting about how we detect asteroids. So I'm gonna give you a couple of questions we received from our participant in social media.
okay, that's
So
fine.
the first one,
That's,
okay, the first one, which is the
yeah.
difference between asteroid, comet, meteor, and meteorite.
So if you look at the comet would probably have a tail, not only one. It can develop many tails. So if you look at pictures of comets, you can see that they have a tail, and the tails comes from the solar wind um, that is taken uh, is fragmenting the comet. And if you look at asteroids, asteroids do not have asteroids are rocky or it has higher metal composition. So the solar wind probably does not affect as much as it affects a comet. So that would be a difference. So you would say the comet has tails, and asteroids are rocky and are or composed of metals, and therefore they do not disintegrate fully like a comet while approaching the sun, for example.
Mhm.
That would be a difference.
Okay, the second question,
So
Jorge,
also,
what is the risk of
okay,
impact with asteroid?
I'm sorry. Can you repeat the question, please?
Yeah, I said the second question was what is the risk of impact with an asteroid?
What's the risk? Well, the main risk is that we can actually got a massive extinction. Like I was showing in the first slides, we have a massive extinction on the first on the stage of on the geological period called the Cretaceous period. We got a massive extinction. What it meant was that the dinosaurs are no longer with us. so so a risk of an asteroid impacting the Earth is massive extinction. The main reason why we're searching these asteroids are because of this. And however, there are situations in which an asteroid impact could be less risky, like it can cause perhaps can cause a global environment catastrophe, which is less risky than than, affecting the whole orbit of the Earth, for example. Or it can cause localized effects, like it can cause a local environment, let's say in a region of the Earth and not the whole of the Earth. So asteroids are a risk because of this. They can cause massive extinction. They can cause global environment catastrophe, this is actually technically called impact winter, and then they also can cause localized regions impacts and, and catastrophe, environmental catastrophe in only in regions. So I would say that. So are
Mhm.
there any more questions?
Yeah, we do have a question from Marwa. She say, how we calculate the orbit of an asteroid and how often we can see asteroid in the sky.
Well, concerning the orbits, I did not actually uh, talk about that today. I have it here, but I'm not. I don't think we can go to it now. But uh, calculating the orbits of the asteroids is a matter of subject matter of the science of I would say photometry. So you would take measures of their path along the sky, different let's say pictures, and then you got a lot of geometrical methods for which you can actually determine their orbits. But since I have not shown this today, maybe a subject of another talk. But so essentially, what you would do is take many measures of their positions in the sky. So you would say this object was here, this object was there in another moment, and then you can like guess what the orbit would be with their orbital parameters. So you got their axis, and then um, their closest approach to Earth, to the Sun, sorry, and then their farthest approach, and then you can round their orbit. But I have not shown this today. And the other question was, you say,
Yeah, the
Melissa,
other
the other
question,
question
how
is,
often we see asteroid in the sky?
so how often? Very often. As I was showing, each month we have 2,000 asteroids discovered. So how often? Very often. Very often. Each day, perhaps you can see 5 10 asteroids. But I'm talking about new asteroids. So each day, probably we have, uh, you know, maybe 60 objects, new objects being discovered. However, if you look at a clear night sky, um, you can see, for example, some of the asteroids of the main belt, like Sirius, like Vesta, like Pallas, like Igea, you can see them because they are of magnitude 7, I believe. So perhaps with a binocular, you can see them. And as well, uh, if you got more sophisticated instrument, if you got a telescope that it has the proper settings for looking at asteroids, so you will be able to see asteroids that are farther away than Ceres and than Pallas, than Vesta. But of course, how often? Well, very often we discover them, and as well, you can actually go and on this night and go and look at asteroids that are already there, discovered there, of course, hundreds of years ago. So, any more questions that you have?
Yeah, another question from Ayman. He say how we can protect ourselves from asteroid.
Who can? Okay. So again, I did not talk about the subject matter that talks about that is deflection of asteroids. And well, there are many proposals for deflecting asteroids. So people say, for example, some people say, I believe people from the MIT in the 60s, they were thinking about this, and they got a name for this project called Icarus, I believe. So they would send a space proof and explode asteroids. So, so by means of explosion, we would get rid of the asteroid that is posing a risk to Earth. But this is risky because when you split an asteroid, when you fragment, and then you can get many small pieces of an asteroid, and they can still come to Earth. There are other methods which involves creating or deflecting them by means of the light. So you would swiftly change their orbits, for example. But I believe that we do not still have like a plan properly set it up to say we can deflect an asteroid. I believe there are there is research on this, but I'm not sure about that. So, any more questions on that?
Yeah, we do have other question from Dorothy de Alba. He said, "Do you think that the Chelyabinsk event symbolized us in this subject as society?"
If the event, I'm sorry, if the event can you repeat?
Yeah, he say that, do you think that Chelyabinsk event symbolized us in this subject as society?
So I cannot hear your question. I think if you could again repeat, please.
Okay, I said, okay, I'm gonna write it for you in the chat because, yeah, I think the connection is not good. I will write it for you in the chat.
Okay, that's fine.
Okay, it's in the chat.
In the chat. Uh,
In the Zoom chat.
yeah, I know. Okay, let me. Okay, it's in the chat. Okay, so it says, "Do you think that you sensibilized us?" Okay, and this is just society. Yes, of course, because it was more recent. Um, However, the mean that I did not actually mention event that happened just recently was the Tunguska event. And sorry for not mentioning, I forgot it. This happened in the year 1908, I believe. Yeah, I think so. And this event was um, allegedly was an asteroid, and this asteroid go through the the forest of Tunguska, which is in Russia as well, and this happened 100 years ago. So from that point off, like many people start to believe that perhaps we should take care of asteroids. So it was 100 years ago, and however, the Chelyabinsk event, this event just recently happened. It happened 7 years ago, and concerning the politics of this, NASA actually had a law of an American law, so they what they call a mandate. So they were compulsory. They should or they had to be able to discover all of or 90% of the objects that threatened the existence of life, and the year that was issued, this was in the 1991, I believe, 1991. So the Congress of the United States say, you gotta discover all of the asteroids that are threatened, that can threaten the life on Earth by the year 2000. And so I believe that they did this by the year 2011. So by the year 2011, NASA has discovered 90% of the objects that threaten the existence of life. So this Chelyabinsk event happened afterwards. NASA already had discovered all of the objects that threaten our life. So, so actually, so yes, Chelyabinsk event sensibilized us, but we already knew this was this is this can threaten life. So we knew this from 100 years ago. Uh, so I would say that just we are just more just recently this event just affected us, but we already knew that that is a threat to life. So
Okay,
any
for
more
me,
questions?
yeah, I have a comment. I would like to back to your slide 30, 30 in the presentation.
Okay, so let me open again, but I think yeah. So yes, this one, so I should say. So the slide about Pluto.
No, but there are like two images there about the the observation of asteroid in the sky, first and second image.
Okay, let me share again the screen so we can see sharing with you. It should be so the one that talks about the triplets or
Number 30, 30.
30 is this one. Yeah, this is
Yes,
about Pluto. So
yeah,
so your question would be or comment, so you say
yeah. In fact, is a question or comment. Okay, for example, in the picture of January 23 in 1933, if we look to the
yeah.
position of that bright object, if we try to imagine the orbit of the object, it's somehow like it seems for me strange because if we look to the orbit, like where it was first in the image in the left, and then how it become in the image of in the right, the orbit is like that, is like too much acute. So is that something
Okay.
normal for asteroids, like have acute orbit or ellipsoid orbit?
So okay, so acute no. So I would say there are many families of asteroids, and you got audits that are, as you say, acute on some of the families of asteroids, but this is planet Pluto, and or what we call planet Pluto, which now is a dwarf planet, and
Mhm.
then uh, actually, um, I think maybe the image, maybe you're right, maybe the image is a bit like it's not properly like tilted, but this image is actually is an image of the same field of the sky and at different times, of course, and so yeah, perhaps it looks. The thing with this is that it's very
Even if it's for a
reduced.
planet, the orbit's still really weird somehow.
Mm, but I think I would say that perhaps it looks like that because on the would you say the field of view is I would say it's a small field of view. It's just
Mhm.
perhaps this is just 1 degree or something like that, and so it's very reduced, and so I don't know if so I could actually. So the thing is, I don't really know. So perhaps I will look what you say, and I will ask to somebody that perhaps maybe he knows this. So and I reply you to that because I don't really know, but I can see your point. I can see that this it looks like it's very acute and it moves in a very acute angle. So perhaps you're right. So I will check with this person and then I will come back to you. Somehow.
So I don't
So
know
I'm
if
sorry
our
about that.
participants have some question here.
Okay, that's fine.
I don't know if someone have a question here in the Zoom. Okay, since we don't have any more question, I would like to thank Jorge again for the nice presentation about how you detect asteroid in the frame of Asteroid Day. Thank you, Jorge, and I'm sending you greeting from Italy, and let's hope that we can meet another talk.
That's fine. Thanks so much for having me today, and let's perhaps see you in another day,
Yeah, perhaps. Thank you. Bye bye,
another talk.
everyone. Bye bye.
Thank you. Bye bye. Bye bye.
Bye.